In this teaching object, we're going to take a look at buffer overruns as well as some of the tools and techniques that can be used to avoid them. To begin with, what is a buffer overrun? Well, a buffer overrun most often happens when there is a buffer in memory that is inadvertently overwritten by data that exceeds the length of that buffer, and in the process overwrites other values. Most often, those other values will result in the code jumping into a arbitrary location in code to begin executing, or possibly even by injecting that executable code itself and then tricking the return value of a method to run that code directly. Given the low-level memory management required to be able to write code that can be exploited in a buffer overrun, it most often exists in unmanaged code such as C and C++ code. Buffer overruns can occur in static buffers, in heaps, and vtable function pointers, as well as exception handlers. The most common place you'll find buffer overruns is in using the execution stack. Buffer overruns are probably the most common and most dangerous security risk available today, partly due to the fact that there is so much native code that exists in production environments, and partly due to the fact that these can be difficult to track down and difficult to address. The most famous exploits that have occurred include the Internet worm of 1988, which nearly knocked out the entire Internet, as well as the Code Red worm, which resulted in a significant slowdown of Internet activity in the late 90s. Developers will often find that if they're not careful, their applications may end up on the next list. I mentioned that stack overruns are the most common way for buffer overruns to be exploited. So let's take a look at what's supposed to happen when a method is called. To start with, the return value of that method or rather the return address of the instruction calling into that method is pushed on top of the stack, so that way when the method is done, it can return to the value in the method that called it. Next, any local variables are set up on the stack by incrementing the pointer in the stack in order to make room for them. And then, after that, any kind of business logic that might occur happens inside the application itself. However, there is always the risk that in some of these cases you could have an overrun. So this is the location where most of the focus should go on, is to be careful as developers are writing code that may impact variables that are on the stack, such as in this case, the local variable buffer. However, assuming everything goes well, at the end of the method, the stack is cleaned up, the return value is then taken, put back into the instruction pointer register, and execution code continues at the point before where this method was called. So now let's take a look at how the stack works in action. We'll switch over to Visual Studio, where we have a very short application ready to go. In this application there's a main method, and that method has a buffer in it. There's also a second method called foo that takes in a buffer, copies that buffer using memcopy, and then returns a value of ed hex. We're going to jump right into this, so I will choose to debug this application. And I've set a breakpoint on the call to foo here. So now that we're inside main and the application's run, we have a buffer that's been set up, and I'm going to go over to the memory pane here, and I'm going to type in buffer, which is the variable name, and it's going to bring me to that location in memory, which is part of the data section of the stack of our application. Now I'm going to scroll a bit up in order to give us some more room to look at. Now at this point, the stack is roughly in this location, or the stack pointer. In fact, if we move up here, we can see exactly where the stack is indexed to. When we call into this foo method, the main thing that we're going to be interested in is keeping track of the instruction pointer. Now the instruction pointer here is kept in a register that tells the processor which address in memory should be used next to return the value to be processed as an instruction of the application. So in this particular case, we're looking at 00411659. Now if we step into this method, you'll see that this will be incremented to point at the next instruction, and that value will be put onto the stack. So I'm going to go to the debug menu, and I'm going to choose to step into. And you can see that the instruction pointer has changed here because we've called into a method. But if we take a look at the stack, and we'll step forward once more. If we take a look at the stack here, there is a value here. Now this, keep in mind, this is little endian, so this value is actually 00411662. This is the instruction pointer that's being saved on the stack. Before that, we have all the information we had from the parameters that were passed in this case buffer. So if you see mousing over buffer, it is 0013FF5C, which is this value here. And this value here represents our data that's on the buffer right now. So if we perform a mem copy, so we'll step over this, and you'll see that there is data here now that has been copied in, because this is the pointer we're looking at. If we mouse over my buffer, you'll notice that it gives us the value of 0013FE8, which is here. And this has just been mem copied. Now the return value is going to be returned via the EAX register here. So if I step over, and then step over one more time, that value is the return value is put into the register here. The stack was cleaned up, and the instruction pointer that had been pushed onto the stack, 411662, was taken off the stack, put back into the instruction pointer register, and we were back inside the main function and ready to run. Now, of course, in this particular location, imagine, given the place in memory that we had been looking at, which was up here, suppose instead of copying only 10 bytes over, we had copied over quite a few more bytes and had inadvertently overwritten this instruction that we were just looking at right there. That's what we're going to take a look at later on in later demos. Now let's pretend in that case the scenario we talked about where we had overwritten more values had occurred. First we would call into the method. The return value would be pushed onto the stack. Then we would set up our local variables. Those would get pushed onto the stack. And next we would call string copy, only at this time it would overwrite the values on the stack as well as the return address itself. Then when the method ends and the stack gets cleaned up, all those values get pushed off the stack, and the return value is then taken and put into the EIP register, which unfortunately would be a buffer overrun because that would very likely point to a different location than it should. What happens with a buffer overrun? Well, if you're lucky, you just get an access violation error, and the application will be shut down by the operating system. Of course, there is a risk here in denial of service against servers because of the fact that shutting down an application and restarting it, if you're able to restart it, is providing a very poor experience for users. And in the event that the application can't be restarted at all, then the users can't get to the service at all. If you're unlucky, you'll get some instability because buffer overruns can be pretty difficult to track down. However, if you're really unlucky, the hacker can maliciously inject code and then execute it using the same privileges and everything else and resources that the process has access to. As a result, one of the ways to mitigate against buffer overruns is to use the principle of least privilege and use least privilege accounts to run processes, but of course it's also very useful to do everything possible to avoid buffer overruns to begin with. So now let's take a look at some code that has a buffer overrun in it, and let's exploit that code to show what it's like. So we're going to pick a different project here, and we're going to open up some code we've got. Now this code here, in fact, we'll just go ahead and we will take a quick look through. All it does is it starts off by taking a buffer here and filling the buffer with a bunch of data. This data has a bunch of characters in it to overrun a 10-byte buffer that'll be on the stack later on, to overwrite the block pointer, and then take the address of a bar method, which is being pulled out of memory, which is the location of this method here, and putting that directly into this buffer as well. So if we run the application, it'll push all this data into this buffer here, and then it's going to call the foo method with that buffer. Foo, as you may guess, has the risk in it of the exploit, so we have only a 10-byte buffer on here, and as you can see from what we had copied below, not only do we have 10 bytes as well as 2 padding bytes here, but we have extra bytes to overwrite the block pointer and then finally overwrite the instruction pointer in memory, so that when the application finishes after the string copy, it's going to return. The return address will be the address of bar, and we will not be able to recover from that. So we're going to start off and we're just going to run the application without debugging. We start off by here by taking a look. It says we're entering foo, and shows what the stack looks like. And you'll notice that we have a block pointer here, and we also have our return address here that was saved, as well as the parameter for input and some other random data below that. After that, we perform the copy with string copy, and then you'll notice the stack overwrites the values of 0 through 9 that we had set up, and then there's also a couple extra values that were added in there as periods here, these 2e and 2e, and then we're overwriting 2e, and then it says EBP for these guys in reverse order. And finally, the address of bar has been injected to overwrite the address that was supposed to be used to return from this method. And then it ends at that point because this happens to be a null value here. Sometimes as a developer you might luck out and that your memory will align so the way you have more nulls inside different parts of the application, but you can't rely on that because obviously it's not something you can cause to happen intentionally. And then finally, when the application tries to return from that method, you'll notice it enters bar, and it says, "Oh no, I've been hacked here." There's nothing we do to actually call into bar directly. It's just that that's where the instruction pointer was, and as a result, when it returns, it comes in here, calls a method, and then exits out directly. So this is an example of a buffer overrun that is not protected in any way. So how can you go about protecting against buffer overruns besides writing code that is free of the exploit itself? The first thing to look at is the GS switch that's part of the C++ compiler in Visual Studio or in the Win32 SDK. This compiler switch is intended to guard the stack from potential overruns. It'll detect these overruns by inserting a 4-byte value known as a cookie at the top of the stack, and if that cookie changes before the method returns, it's clear to the application that the stack was overrun. You can also set up security handlers that will be called in the event that a buffer overrun is detected. Otherwise, what it will do is it will just close the application but after showing an error dialog. Now keep in mind that this does not fix overrun problems, it merely detects overruns that might occur and stops them before they do real damage. The good news is that this is on in Visual Studio 2005, and if you want to turn it off, that's possible, although I don't recommend doing that except for cases such as demonstrations like this one. And in earlier versions of the C++ compiler, you just had to add in the /gs switch. This is a switch designed for native applications and I don't believe it's compatible even with managed code development. So with GS, let's take the example we've been using all along, where we have an unsafe method. And when this method gets called, the return address gets pushed onto the stack, and then the GS cookie gets pushed on right above it. Afterwards, the local variables will get set up on the stack in the same way. Any business logic will occur, and in the event that the GS cookie gets overwritten, whether or not the return address gets overwritten, that'll be detected when the stack gets cleaned up. It'll either pop the dialog or it will call your security exception handler, and then you'll be able to either recover from that or feel better about the fact that the buffer overrun was avoided. Now there is one thing to keep in mind in that GS 32-bit value could theoretically be overwritten with a value that is exactly the same. Obviously it's a 1 in 4 billion chance, but it is possible to happen. And so as a result, it's not a completely perfect solution, but it's about as good as you can get. So let's take a look at some code that uses the /gs switch. And this code here is actually the same code as we had in the previous solution, and I'll just open it up real quick to show you. The only difference in this code here is that it's being compiled with the /gs. So if we go to run this application, the application will run and it'll actually stop, and we're getting more detailed data here because I'm running it in debug mode. So what I will do is I will close this out, stop debugging, and I will tell it to start without the debugging. And you'll see that we've actually run through and it's been hacked. So I will set this as the startup project since the wrong project was set up. We were running buffer overrun, the first project, the previous demo in that example. So this time we've got the right project selected, and from the debug menu I will choose start without debugging, and it runs, and you'll notice it pauses here, and it's going to pop us a dialog box here that is a very user-friendly dialog saying there was a problem, we'd like you to send data to Microsoft so that they can provide it back to the software manufacturer so that they can fix it. This occurs because of the fact that the GS switch was triggered. And if we take a look at the code here, you'll see that on the stack right below some of our values, we have a GS cookie, then we have the EBP, and we have the return address. And then when the overwriting is done, the GS cookie gets overwritten, and this value is a random value that's generated by the compiler. In this case, we're fortunate in that the value that was overwritten with was not the same as the random 32-bit value, which will happen in most cases. You'll be pretty safe in doing that. And as a result, we were able to avoid having the bar method called and inadvertently running code that could have theoretically been malicious. So now that we've talked a little bit about how to protect this at runtime, let's take a look at the safe string handling library that's available that provides some safe string handling methods that can be used in order to mitigate some of the risks at development time. One of the key things about these string safe libraries is that the size of the destination buffer is always provided to ensure that you're not going to overwrite that into the buffer. The important thing about these methods is that every one of them takes that destination buffer size, so there's never ambiguity as to whether it's the number of characters, the number of bytes, the size of the buffer, the size that's remaining in the buffer, or any of those other things that you might find with standard C++ routines. Another nice thing about the string handling libraries from StringSafe is that they're guaranteed to be null terminated even if the operation truncates. So if you're trying to copy 50 characters into a 10-character buffer, it'll copy 9 characters and then terminate that with a null character so that you can be confident that the return buffer you're getting is safe to use. All functions will also return you an H result instead of returning whether it's a pointer or an integer or other value. So you can always use the success code, being S under OK, to be sure that it succeeded, or one of the possible error codes that we'll cover later. Another nice thing about this is each of these functions is available in both character count and byte count modes in order to provide an easier way for you to differentiate between character operations and byte operations in code. There's all kinds of methods that exist today, ranging from your string cats to your string copies, as well as your string lengths. And each of these has a counterpart in the string safe library. If you can't find the counterpart, just do a search on MSDN for the method that you would use, and there's a very good possibility the string safe counterpart will show up, and you'll be able to get to this table. So this table was taken from MSDN, and it shows the character count methods. There's also the byte count methods, and these as well provide a great way to copy across. These are both available as ANSI and Unicode, and if you use the base that does not have an A or a W at the end of it, the compiler will select the right one based on whether Unicode has been defined for the application or not, and how the headers handle that. To use StringSafe, very simply, you #include stringsafe.h to files that might manipulate buffers. Anywhere that you would use a string copy or a mem copy, and then you can go through your code manually and make the updates. Or one of the things that it's kind of lazy to do, but it works well, is to look at the flagged methods that occur when recompiling, because all of the deprecated methods, such as string copy and string length and string sprintf, will be marked as deprecated, and so those will get flagged by the compiler as warnings. And you can actually walk through the window inside Visual Studio and manually fix each of those. It's not the most proactive solution, but it is a good way and an easy way to take existing code and to port it over to use stringsafe.h. You may also need to link against stringsafe.lib depending on what version and how your project was built to begin with. If you're creating a new project in Visual Studio 2005, this should already be as part of the link package. So let's take a look at applying StringSafe. And what we're going to do is we're going to take an application that already has this set up in it, and we're going to set our startup project to be the third project in the solution. And this is a project that really does everything that the other ones did that we were showing, the earlier ones. The only difference here is that we're using a string cch copy A, which is the ANSI version, in order to copy the values from our input buffer into our new buffer. As a result, we can run this application. So we'll just run it real quick, and you'll see that the stack to begin with looks like the stack always has for all these. demos we've shown. The one difference is that we don't have the GS switch turned on here. We've explicitly turned that off, so there is no GS cookie being inserted, because we wanted to show that as the application goes ahead and uses the string safe library in order to do the copy, 9 bytes were copied across using the ANSI method, so that's 9 characters, and then it was null terminated, and then there were 2 padding bytes that were just part of the way the stack set this up as well. So even though we didn't explicitly think to check whether the input buffer was smaller than the buffer we were copying to, the string safe library was able to protect us there by adding some checks in for us. Now, often we get asked the question, why would I use string safe libraries instead of the end functions? For example, C++ has standard routines such as string ncopy, string ncat, as well as ANSI and Unicode versions of those, or rather, as well as Unicode and wide character versions of those. Why wouldn't we just use those? And the fact is, yes, you could use those and it would be safe, and you could also use the regular string copy methods as long as you checked to be sure manually that the lengths were going to appropriately line up. However, something to be careful about is the count parameters of each of these methods indicate different values. In the end function, such as strncopy, you're looking at the maximum bytes or characters to copy, whereas the string safe functions always will expect the total number of bytes or characters in the destination buffer, depending on whether you're using the bytes or the character methods. String safe also has end functions as well, that will take both the length of the source and the length, or rather the length of the buffers as well as the number of bytes or characters to copy. But typically, you'll probably end up using the ones that are not the end functions. Another key thing about using string safe is that it's very intuitive to use them correctively. Whereas it is very easy to make a mistake when using the end functions, or unfortunately, it will be anti-productive to use them in the right way in some scenarios. So if we take a look at the definition of WCSN-cat, this is the wide character version of string cat, string ncat rather. So this is a relatively safe method as far as the C++ routines go, in that it takes in, if we take a look at the first parameter here, it takes in the destination buffer as a pointer. The second value is it takes in the buffer you want to concatenate with, so the one you're going to add to the first buffer. And then it takes a count, which is the number of characters to concatenate. As in order to make life easier for developers, this method also returns a pointer to the destination buffer itself, so that you can concatenate the calls in code in order to save space. Of course, you'll want to be super careful whenever doing anything like that, because it's very easy to make accidental mistakes and inadvertently result in buffer overruns that could occur in different ways than expected. So let's take a look at what the string CCH-cat definition is like. Now, this is not the end version. This is just the standard string cat version from the string safe handling library. This returns an H result, as we talked about. All the string safe methods return an H result in order to remain consistent with each other. The first parameter it takes is just like in the end functions, is the buffer to concatenate onto. Now, the second one, though, is the maximum number of characters that can fit into the destination buffer, and that accounts for the null character at the end. So if you create a buffer that is 64 characters, you can pass in 64 as the value here, and then the string cat method will know that it can copy in 63 characters and then null terminate that. And then finally, the third parameter we have here is the buffer to concatenate with. So let's take a look at using the WCSN copy and the WCSN cat code in order to write some application code here. The first code we have here, the bug might be pretty obvious. We're indicating the total characters to copy and not guaranteeing a null terminator. So if we start off the first line of code being the copy, we're going to copy 10 characters into that buffer, and that buffer variable is not going to be null terminated. So as the first bug we're dealing with here is that we have to be careful about the non-null termination that's going to happen. So we'll change that to say that we want to just use the size of the buffer minus 1. This way we can save some space. Now some people might argue that we want to put 9 in there, but there's actually a reason that wouldn't work as well, is that teachR might be a single or double byte character depending on whether or not Unicode is defined. If it's a double byte character, then size of buffer -1 would be 19, causing a buffer overrun. So we would want to put in explicitly something to account for the size there. So if we account for the size, and we take the size of the buffer and divide it by the size of the first element in the buffer and subtract 1 from that, then we have safer code when it comes to dealing with the copy. But we're still not out of the woods yet, because since the source buffer still has more characters to copy, the destination buffer still won't be null terminated. So we don't know what kind of data was in buffer to begin with, since it's not going to be initialized. So it could possibly be initialized with all null values in buffer, or it could have other values, and perhaps the 10th character in buffer is not null, in which case we're going to copy over 9 characters in our WCSN copy, and then that 10th character is going to be whatever garbage character might have been in there to begin with, and we're not guaranteed a null terminator. So what we can do is we can memset the buffer to begin with and say that we want it to be all nulled out, do the copy, and then have the concatenation. But we're still not quite there yet, because the count that we're using on WCSN cat tells us how many characters we want to copy there, and doesn't take into account at all the size of the destination buffer to begin with. So we want to adjust that to keep track of the size of the buffer when we make the call in, and finally, when we do the concatenation, we want to be sure that we only concatenate the number of bytes we could possibly copy forward. This is code that I believe to be secure, although it is possible there might be another case we haven't considered here. But as you can imagine, writing this code and debugging it and trying to figure out what it is could be a huge challenge. So there really must be an easier way, which is why I always recommend using the string safe libraries instead of using those end functions. In this particular case, we're saying we want to copy the buffer across, and then we want to concatenate the buffer. If we go to execute this code, what will end up happening is the copy will copy the first 9 bytes in its source buffer, being 1 through 9, and then it'll cut off that last 0, it'll null terminate the buffer, and then string cchcat will be called, and it actually won't do anything because there won't be any space for it to copy any data into the new buffer. But fortunately, this is very secure in that as long as we're aware of the size of the buffers we're working with here and the amount of space we're working with, we're going to be in pretty good shape. Note that you'll still have to be very careful with the size of the destination buffer, since overruns are still going to be possible, but fortunately they're much easier to prevent because there are very few issues you have to worry about when dealing with the string safe libraries, whereas there's many things you have to be careful with end functions. It's also good to be aware of the string safe return values. We did not look at those in the last method, in the last example, although we probably should have, just to have provided more robust code. But if you get S under OK, you know that the operation succeeded as documented and everything's fine. If you get the invalid parameter return code, it's probably because the buffer was either already full or, unfortunately, a null would have been passed in. And this is better, of course, than a null exception that would occur, or rather just crashing the application by trying to write to that location in memory. And then there's also a nice middle ground here, which is the insufficient buffer return code. And this will tell you that there wasn't enough space for the whole operation, but it copied all the data it could and null terminated the destination buffer. In our previous example, the string copy would have returned the insufficient buffer return, and then the string cat would have returned the invalid parameter call. However, neither of them would have failed necessarily because they were doing exactly what we asked them to. There just wouldn't have been enough space. It's generally a good practice to look at these return values, because you may find that in the case of an invalid parameter or an insufficient buffer, you'll be able to detect an attack against the system. So sometimes it's a good idea to log that to determine if that's what's going on. Another great way to avoid the risks and dangers of buffer overruns is to use managed code. Managed code here I'm referring to is .NET Framework application code that's managed by the Common Language Runtime. The .NET Framework is available as a free download from Microsoft, and Visual Studio has great support for building applications for it. And you're able to port existing C++ applications to managed code simply by compiling with /CLR. Managed code itself does a lot of work to prevent buffer overruns through mechanisms such as type safety, bounds checking, and some of the execution flow enforcement that's provided in there. It's very important to realize, though, that the managed code manages managed code only, and that there is code that exists outside the realm of managed code that may be part of your C++ applications that is not under the jurisdiction of the common language runtime. So it's important for us to cover the fact that it is possible to write applications that will be buffer overrun safe, which we'll do here. And what we have is an example here of managed code. And this code here, instead of using any of the native classes and libraries, this uses an array of characters. In this case, we've got an array of 22 characters. And it uses the copy_to method. And this is a managed array, I should call out. And there's a string being passed in, which is a managed string. And we're going to do a copy_to from the string, where it's going to copy into the buffer, and it's going to copy the number of characters that are available in the string, and then it'll tell us whether the copy succeeded or failed. So if we set this as our startup project, we're going to go ahead and we're going to run it, and you'll notice we get an error here that tells us that the copy failed and that the index and count must refer to a location within the string. Now this exception that's occurring here is actually due to the fact that it's trying to write past the end of the buffer. Remember that when we created this buffer, we created it with 22 characters and not 23. So if we go ahead and we're going to delete and we're going to replace the 22 with a 23, we're going to run the application, and you'll notice the copy succeeds because the buffer was big enough. Now, and we've just shown a very simple example here of what happens when the exception gets thrown, and we're actually catching a generic exception here, although you'd want to be more specific. But this is a very nice thing to know, is that you don't have to really be concerned about what happens in managed code when you're dealing with managed objects and managed data, because the common language runtime will enforce that for you. However, I do want to cover some of the caveats of working with managed code. The first two here, the first one is that the .NET Framework is required on the client machine in order to run managed code. So there could be potentially a deployment hit there, although the majority of Windows machines out there today do have the .NET Framework installed via Windows Update or via other applications. Secondarily, there is a possibility that running in the CLR could hinder performance. But there is also an argument that says for certain applications you can get potential performance benefits because of the optimized JIT compiler. At the same time, there's also mechanisms such as NGen for you to pre-JIT an entire application into native code and then install that onto the client machine during installation time, which can also mitigate any of the managed code risks. Now the third bullet here about the CLR not enforcing the execution of native code is the most important security caveat that you need to be aware of. There can still be buffer overruns even if you're running a managed application because of what happens when you call into native code and components or when you use native data. You'll also need to be aware of interop marshalling, such as when you use p-invokes or other kinds of calls into com-callable wrappers or other ways of interoping with native code, because types are not enforced across those boundaries. So there is always a potential risk that the wrong type could be passed in or that other problems could arise. So what I'm going to show you here now is a very basic application that shows an unfortunate buffer overrun that occurs in managed code. Now this is a buffer overrun that's not occurring, it occurs in a managed application. This is not a managed code buffer overrun necessarily, it's just that we have managed code here that's using native data and native execution paths. So this is the same application that we were showing in the first few demos to take advantage of the GS cookie as well as the buffer overrun, only this is being compiled and run as a native application. So if we go ahead and we start this without debugging, you'll notice that we do get the same thing. Now the stack was set up a little differently, in which we can show you that we're dealing with some data here that is managed code, because there is more stuff that's required to set up a method call. But the application itself still allows you to overwrite native data in a native method, such as string copy, to overrun the buffer with the address of bar. So it just goes to show that while managed code can provide a huge benefit to developers in security, you still need to be aware of any kind of native interop and native code you're going to have, or native data you're going to have in those applications. There's some security tips we'll provide for managed code, which involve locating calls to the unmanaged and native components that will be used by the application itself, as well as checking strings that are passed into unmanaged APIs. As I mentioned, it is possible to call into code and send the wrong values in, or to send values in that result in a native buffer overrun. And this can also happen with file path lengths and output values as well as array bounds. So to take a quick review of this teaching object, it's highly recommended that you're wary of using certain functions, such as the standard C routines or some of the deprecated Win32 routines that are used in order to manipulate memory that could theoretically have a buffer overrun, whether on the stack or in the heap or in other locations. It also definitely double and triple check all those parameters. Some of them ask for characters versus bytes. Some of them will ask for the count versus the size. Some of them will ask for size left. And you need to be aware of all the different possibilities if you're going to be using some of these functions. The easy way to get around that is to use string safe for that safer buffer handling. There's really also no reason not to use the GS compile option in Visual C++. It doesn't replace the need for careful programming, but a combination of string-safe handling libraries with the GS compiler switch can drastically improve the security of your application, given that it will help you at both design time and run time to have better code. And then, of course, if it's something that's within your realm of options, go for managed code. Managed code is a great way to build applications that can be very robust and reliable. But also, when using C++ CLI or the managed extensions for C++, you'll find that you can get all the benefits of flexibility of accessing native components, and yet all the benefits of using managed components for better productivity, as well as some of the security enhancements you can get from the .NET framework. Thank you.